Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Pharmaceutical Organic Chemistry Paper 3. In the Unit 2, we will be studying about stereoisomerism Part 2. In the first lecture, we will be studying about geometric isomerism. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. The topics that will be covered in this particular session includes studies about geometric isomerism, what is the definition of geometric isomerism and what are the different types of geometric isomerism, what are cis-trans isomers, what are EZ isomers, what are SynAntinotation. All these details we will be studying. We will also be studying about the comparison between the three types, under what circumstances we will be using cis-trans isomerism. The nomenclature as cis-trans isomerism, EZ isomers or SynAntinotation will be discussed. Let us start the next session. In this session, we will be studying about geometric isomerism. So what are geometric isomers? Geometric isomers are molecules where certain groups or atoms are fixed into their spatial position with respect to one another. This happens due to the restricted double bond rotation, or it may also happen in ring structures where there is a restricted bond rotation. So the general nomenclature which is commonly used include cis-trans isomers or EZ isomers or SynAntinotation. So these are all the different nomenclatures that is used to describe geometric isomers. Let us first start with the cis-trans isomers. So these stereoisomers are given cis configuration if the groups lie on the same side of a reference plane, passing through the double bond and perpendicular to the plane containing the bonds linking the groups of the double bond atoms. So we have two arrangements as shown here. In the first arrangements, there is a sp2 hybridized carbon here, there is another sp2 hybridized carbon here. We can assume like that, and there are two different groups. One is represented as the pink color, another one is represented as a green color. So if these two groups are how they are placed, that decides whether it is a cis isomer or trans isomer. So they are placed across the double bond. So if these two groups are on the same side, then we say cis. Now if you look at this second arrangement, here they are on the same side. Let us say the green groups are also on the same side. So is this arrangement also called a cis arrangement? But the difference lies between the groups should be on the adjacent carbon atoms and not on the same carbon atom. If it is present on the same carbon atom, then there is nothing called cis or trans isomers. If the same type of groups are present on adjacent sp2 hybridized carbon atoms and if they stay in the same side, then we call that as a cis isomer. So extending that, if we say generally terminal alkenes where C double bond CH2 groups are present does not show cis-trans isomers. Why? Because we cannot represent them by a different way. Both isomers, when are hydrogen atoms, whether they are placed on the same side or opposite side, is very difficult to identify. As shown here, generally cis trans isomers are given relative to something. That means one colored group, whether it is on the same side across the double bond or it is on the opposite side of the double bond. That is how we say. But if both the groups are hydrogen atoms, let us say this is hydrogen and this is hydrogen, which is present on the terminal carbon, then what will happen is, with respect to one of the hydrogen, whether the green group, whether let us assume if it is a methyl group, whether it is on the same side or it is on the different side cannot be mentioned easily. So that is the reason terminal alkenes does not show cis trans isomer. The same way, if the alkenes of the type C double bond R2, that means the two groups that are present on the same alkene carbon atom, they also do not show cis trans isomers. And generally alkenes of the type having different substituents show cis trans isomers. So as we mentioned here, same groups present across the double bond from the same side. Same side means if we cut the molecule in this way, that is passing through the double bond, and a plane which is perpendicular to the molecule, then if two groups are on the same side, when we cut the molecule across this double bond in this way, then if these two groups are on the same side, then that arrangement is called cis arrangements. And if the same way, if we cut the molecule across the double bond and the same groups are on the opposite side, that is called the trans arrangement. So this is how we can actually identify whether it is a cis isomer or the trans isomer. So the point to remember is, when we are cutting the molecule into two pieces, what we have to do is it has to pass through the double bond and it has to cut the molecule into two pieces. So not across the double bond, but passing through the double bond. Here some examples are given. We have a malic acid and the fumaric acid. The cis isomer is having a lower melting point and also having lower boiling point, whereas the trans isomer is having a higher boiling point and a higher melting point. The cis isomer is not found in the nature, whereas the trans isomer is found in the nature. And here, because this is a carboxylic acid, so it can form intramolecular hydrogen bonding, whereas in the trans isomer it generally forms intermolecular hydrogen bonding. So that means there is an oxygen here which is having a lone pair of electrons, and there is a hydrogen attached to an electronegative oxygen. So these two can form a hydrogen bond. So that is what is called intramolecular hydrogen bond, whereas in the case of trans isomer it cannot form, because this OH and this OH are actually far away from each other, and this oxygen and this hydroxyl hydrogen cannot form a hydrogen bond. So in this particular case hydrogen bonding is possible, but that is possible only through intermolecular hydrogen bonding. Now let us predict some of the compounds shown here, whether they belong to cis or trans isomer. So in this particular case we have hydrogen and hydrogen. So always we have to have some reference atoms or groups. Based on that we say the groups or atoms are on the same side or on the opposite side. So we have to cut the molecule across the double bond like this. When we cut across the double bond like this, the hydrogen is on the top left, this hydrogen is on the bottom right. So they are on the opposite sides. The same way, if you look at this molecule, the two groups are different. Here we have a hydrogen atom, here we have a methyl group, but we have similar groups, that is bromine atom, and here also the bromine atom. So if we cut the molecule again across the double bond, then what we have is the bromine and this bromine are on the opposite side. So these two molecules are basically the trans isomers, because the similar groups are on the opposite side. And when we move to the other compound, here the hydroxyl is on the same side and the methyl group is also on the same side. In this particular case, both the hydrogens are on the same side. If we cut across the double bond like this, these two hydrogens are on the same side. So these two molecules are also belong to the same category, that is the cis isomer. If we look at these two compounds, if we cut across this bond, but unfortunately this carbon and this carbon both have the same type of groups, that means this does not show cis trans isomers, which we have already seen. The same way, if you look at this molecule, this carbon has both methyl groups on the same carbon, so that means this compound also does not show any cis trans isomer. The problem why we cannot show any cis trans isomer is we are actually using this as a reference. So in this reference, what we say, this methyl group and this methyl groups are on the same side. That is what we say. And this one of the hydroxyl is present opposite to the methyl group. That is what we can say. These are all only the reference or a relative configuration we are telling. But if we take this molecule, how do we say this aldehyde group is present? Whether this aldehyde group is present on the same side of this methyl group or on the opposite side of this methyl group is very difficult. We cannot actually predict exactly. So that means these type of compounds cannot be given any cis trans isomer. So that is the reason we cannot predict anything. Now let us move on to another type of compound. So in this compound, what we have is, we have a NH2 group. In this carbon also we have a NH2 group. We have a bromine, we have methyl group. So if we have to give assignment like a cis and trans isomer for this compound, and we have two hydroxyls on the same side, and for this compound, so how do we assign whether this is a trans isomer, since both the NH2 groups are on the opposite side, and in this particular case both the hydroxyl groups are on the same side? Is it a cis isomer? So this is going to be a pretty difficult one, because this is not as simple as assigning cis and trans isomers. The reason is we have two different groups. So in one case we have a methyl group, in another case we have a bromine atom. In this case also we have a methyl group under the halogen atom. So these are different groups, and with respect to that, it is very difficult to say whether these are on the same cis trans isomers or not. So to overcome the difficulties associated with the cis trans isomers, CIP rule, Kahn Ingold Pralog rule was introduced, and according to this rule, we have already seen in the RS nomenclature. So the same rules, the priority group rules, are applicable here also. The atom with the which has the highest atomic number is given the highest priority. For isotopes, the one with the higher relative atomic mass has given the higher priority. And when there is a tie, then we look for the first point of difference to assign the priority. And each multiple bond is counted as single bond to multiple atom while assigning priority. So these are all the various CIP rules which we already know. So the application of CIP rule is mainly for EZ notational system, because the cis trans isomers we had a problem because we were unable to assign the actual configuration for the two isomers. So in this particular case, if different groups are present across the double bond, then how do we apply the cis trans isomers? So cis trans isomer generally fails if we have to assign configuration for different groups. So if we have four different groups, then how do we assign cis trans isomer? It's very difficult. So the EZ nomenclature is introduced for that. According to this, what we say is, for each carbon we have to assign highest and the lowest priority groups. So when there are two groups, we say this is a higher priority group and the 2 is the lower priority group. On each carbon, each sp2 hybridized carbon, we assign the priority. So if the higher priority groups lie on the same side, then we say that is Zaman or the same side isomer, E is it isomer. And if the higher priority groups across the double bond are on the opposite side, then we say it is Entgegen or the opposite side, German term. So this is the E isomer. So in this way it becomes very easy. It doesn't matter whether they have the same groups or different groups. We can always assign E is a nomenclature to double bonds, but cis-trans isomer cannot be easily applied to the double bond when the groups are different. So let us come back to the previous case. Now we know this NH2 group and this NH2 groups. According to our cis-trans isomer, we simply say this is a trans isomer, which is actually the wrong one, because when we start assigning the priority in the first carbon, the NH2, the nitrogen and the carbon are the two groups which are attached to this carbon. So the nitrogen gets a higher priority. So this is number 1, and the methyl group gets a second priority. And in the second carbon we have bromine and NH2. So between bromine and nitrogen, the bromine gets the highest priority because its atomic number is higher compared to nitrogen. So in this particular case, what happens? The highest priority groups, the nitrogen and the amino group and the bromine, both are on the same side. So this is a Z isomer and it is not the trans isomer. When we extend the same to this dihydroxy compound, so in this particular case, in the first carbon, the oxygen gets the highest priority and the methyl group gets the second priority. Whereas in the second carbon, chlorine is having higher atomic number compared to oxygen. So chlorine gets the highest priority followed by the oxygen. So that means this isomer, both the high priority groups are on the opposite side. So this is a E isomer and it is not the cis isomer. So this way the EZ nomenclature actually helps us assign the correct configuration without any difficulty or confusion, whereas cis trans isomer always leads to confusion. So that is the reason this is the EZ nomenclature is the most preferred one for this stereo description. Now if we look at cis-trans in other double bonds, basically we have imines, oximes. Basically in the Beckmann rearrangement and other things we use oximes. So in those kind of cases it was an old nomenclature. So still people use oxime as SynAntinotations. We will look at that later. And we also can have a double bond, N double bond and C double bond S are the different places where we can have cis-trans isomers. So whenever we say cis-trans isomer, we actually have to have a reference group in these kind of compounds. So we say with respect to X, the Y group is trans, or with respect to W, the Y group is cis. So we have to always, when these kind of compounds are to be assigned, we always give a starting point or a reference. With respect to that, the other group is whether present in the cis or trans orientation. And in these kind of disubstituted, because this is a tri-substituted one, so that is the reason we are having some problem in assigning cis-trans isomers. In the case of disubstituted compounds, we can easily assign EZ nomenclature because the two groups, whether they are present on the same side or they are on the opposite side, we can easily give EZ nomenclature. And when the compounds have more than one double bond, as an example shown here, hepta-2,5-diene. So how do we assign the configuration to that? We have to go for each double bond separately. So in the first case, this is a hepta-diene. So we have starting from 1, 2, 3, 4, 5, 6, 7. So this is the longest chain rule. So the second carbon, there is a hydrogen, and in the third carbon also there is a hydrogen. So these two hydrogens are on the same side. So this is the 2Z isomer. And when we go to the 4, 5, 5th and the 6th carbon, both the hydrogens are on the same side. So this is again the Z isomer. So this compound is 2Z, 5Z heptadiene. Like that we can assign the nomenclature for this particular compound. And when we come to the second one, the second carbon and the third carbon, if you look at the hydrogens, they are on the opposite side, whereas in the fifth one they are on the same side. So this is the trans isomer and this is the cis isomer. So basically this is Z isomer and this is the E isomer we can assign. The same way when we go to this last isomer, here these two groups are on the opposite side, and the same way the hydrogens are on the opposite side across the double bond in the fourth and fifth carbon. So this isomer is 2E and 5E. So that way we can actually assign Z and E nomenclature when there are more than one double bonds in the compound. And the geometric isomers are also generally show chiral. If a chiral center is present, we can also assign them, whether the Z isomer here in this particular case is these two hydrogens are on the same side, so this is the Z isomer. So this is basically the DL pair or the cis isomer we can also say. And if it is a trans isomer, they are shown like this. So this again is a DL pair. So in this particular case, both the hydrogens are on the opposite side. So this way we can also assign E or Z nomenclature to chiral center, that is the enantiomers, because this is the chiral center present in the compound. The same way here is the chiral center. The next one is SynAntinotation. Basically, how do we represent SynAntinotation is shown here. So the molecule is drawn in the zigzag fashion. So this is the standard way of representing alkyl chain. So the main chain basically in the acyclic compounds are drawn in the zigzag projection, and it has a torsional angle of 180 degree. So like this we just draw in a zigzag fashion. So this is the main carbon chain, and the bonds behind the plane as shown here, this is behind the plane, this is again behind the plane. So these are represented by the hashed line, and the solid wedges basically represent the groups are pointing towards the observer or in front of the plane. So basically, according to Masumane, that is in 1980, if the two substituents of the highest priority are on the same side of the illustration plane of the zigzag projection, so this relative configuration is termed as a syn configuration. And if they are on the opposite side, so this is pointing towards the observer, this is pointing away from the observer, then these two are called as anti-arrangement. Let us look at this molecule in the 3 dimension to see how it is actually represented. Let us look at the 3-dimensional representation of the zigzag notation what we have seen in the 2D representation. So one of the carbon is pointing towards the observer. In the second carbon, if you go from this end, and when we go to the middle one, this is also actually pointing towards the observer. And when we come from the other end, the two carbons which the substituents on the second carbon and the third carbon, both are pointing away from the observer. So if we rotate the molecule, we can very clearly see that. So this one is actually pointing towards the observer, and this one is also pointing towards the observer, whereas this carbon, if you look at, it is pointing away from the observer, and this carbon is also pointing away from the observer. So when we say these two arrangements pointing towards the observer is called the cis arrangements, and this is pointing towards the observer, this is pointing away from the observer, then we say this is the anti-arrangement. The first one is a syn arrangement, and this is the anti-arrangement. And if we look at this carbon and the last one, this is pointing towards the observer, pointing away from the observer. So these two are basically anti-arrangement again. So these two are anti-arrangements. The first one and the third one, these two are actually syn arrangement. And if you look at this carbon and this carbon, This is pointing towards the observer, this is pointing away from the observer. So this is again anti-arrangement. And if you look at the last two, this carbon and this carbon, these two are actually pointing away from the observer. So in other words, these two are again syn arrangement or cis arrangement. So this arrangement was seen in the three-dimensional arrangement. So how these groups are actually present. Let us look at another example. This is hexane 2345 tetrol. So the major difference between cis and trans arrangements and syn-anti arrangement is the cis or the syn arrangement can be assigned to not only to the adjacent carbon atoms but also to the faraway carbon atoms. So this is one of the advantage of using either cis or syn, trans or anti arrangement. So here we don't have to specifically restrict ourselves to the adjacent carbons. They can also be assigned to far away carbons also. Let us look at the first one. Here in this particular case, this is pointing towards the observer, this is pointing towards the observer. So these two, the 2-3 arrangement is basically the cis arrangement. The same way when we look at 3 and 4, these both are pointing towards the observer. So this again is the cis arrangement. And for the 4 and 5th one, if you look at the hydroxyl, both the groups are pointing towards the observer. So this is again the cis arrangement. So that way this compound is a all cis compound. And we can also extend the same if we are comparing between the carbon number 2 and 4. The 2 and 4 is again cis because both are pointing towards the observer. And we can also talk about 3 and 5. This again is the cis arrangement. We can also talk about 2 and 5 where again this is a cis arrangement. So this cis or syn arrangement can be assigned to either the nearby groups or the faraway groups. The same way we can also extend the same to other substituents. So in the second substituent molecule, what we have is the first one is pointing towards the observer, the second group is pointing away from the observer. So this is an anti or the trans arrangement. And between 3 and 4, these both are pointing away from the observer, so that is a syn arrangement. And between 4 and 5, this is pointing away from the observer, pointing towards the observer, so this is a trans or anti arrangement. So the same way if you want to go from 2 to 4 or 3 to 5, both are basically opposite to the groups are pointing, one is towards the observer, another one is away from the observer. So these two both are trans or the anti arrangements. And if you look at 2 and 5, these two groups are pointing towards the observer, so this is a cis or the syn arrangement. The same way we can extend the same to other two compounds. Let us look at these type of arrangements in the 3 dimension to understand how or what we are actually talking in the 3-dimensional way. We can try to see. So the tetrahydroxy substituted compound is shown here. So the first carbon is having the R configuration, and this assignments we already know how to assign RS configuration to this one. So this hydroxyl is basically pointing towards the observer if you look at, and this hydroxyl is also pointing towards the observer, and in this case also, and in this one. So all the cases the hydroxyl group is pointing towards the observer. So this is nothing but the cis arrangement. So we can talk about whether the second carbon and the fourth carbon, or the second carbon and the fifth carbon, or third carbon and fifth carbon. So whichever way we compare, all the groups are pointing towards the observer. So this is basically the all cis arrangements or all syn arrangements. So we can also do the same way if they are actually pointing away from the observer. Then if you look at that case also, they are on the same side. So basically, even though we say pointing towards the observer or pointing above the plane is the only thing, is not the accepted one all the time. We can also have the same groups away from the observer. So basically the cis or the syn arrangement in this kind of situation is relative to how they are present, whether they are pointing towards the observer or they may also be pointing away from the observer. So both we can say. So in this particular arrangement, this is pointing away from the observer. This hydroxyl is also pointing away from the observer. So these two groups are basically on the same side. So whenever they are on the same side, that is a cis arrangement. And here again, if you look at these two carbons, so this hydroxyl is pointing away, this is also pointing away, but they are on the same side. So this again is the cis or the syn arrangement. So what you have to remember is, irrespective of whether the group is pointing towards the observer or the away from the observer, the most important thing we have to remember is whether they are on the same side or on the opposite side. Let us look at another molecule. In this molecule, the first hydroxyl is pointing towards the observer. The second one is actually pointing away from the observer. So these two are on the opposite side. So we can say the relationship between these two hydroxyls are anti-arrangements. And if you look at the third and the fourth one, both are pointing away from the observer. So they are on the same side. So this is a syn arrangement. And if you look at 4 and 5, one is pointing towards the observer, another one is pointing away from the observer. So these two are trans or the anti-arrangement. And if you look at the second and the fourth one, so one is pointing towards the observer, another one pointing away. So these two are basically the trans arrangement. And these two, if you look at this hydroxyl is pointing away, this hydroxyl is pointing towards. So these two are again anti-arrangement. So that way we can actually confirm whether they are syn or anti-isomers. So from the 3D representation, we have actually seen how the cis and trans isomers are actually, or syn and anti-isomers can be represented. So in the case of adjacent substituents, basically the syn isomer is identical to the trio-isomer, while the anti-isomer is identical to the erythro-isomer. This erythro-trio are generally used in carbohydrate chemistry. There are certain exceptions to the syn-anti rule. The most important one is the aldoximes. So in the case of aldoximes, basically the syn-anti and the EZ rules actually change. The reason why this is actually the case is because the aldoximes and the ketoximes are the general names which were used in olden days. So in that time, what people were referring to is whether the ald, that means the aldehydic hydrogen, and the oximes, the hydroxyl group, whether they are on the same side or on the opposite side. So based on that, they used to give whether it is a syn aldoxime or anti-aldoxime. So in this particular case, the hydrogen and the OH group are on the same side. So this is basically called as a syn aldoxime. But if we have to give the EZ nomenclature for this compound, we already know the hydrogen is the second priority group. The methyl group is the highest priority group in this particular carbon. And in the case of nitrogen, we have a lone pair of electrons and the hydroxyl group. So between these two groups, hydroxyl is the highest priority group. The lone pair of electron is having the second priority. So this is number 1 highest priority group. This is number 1 here in the carbon. This is the highest priority group. So according to CAP rule, these two highest priority groups are now on the opposite side. So this is what is called the E isomer. Whereas if we go by the traditional naming, that is aldoxime thing, so this is called the syn isomer. So you have to be very careful when you are assigning nomenclature based on EZ nomenclature or syn anti. The only problem is for the aldoximes and the ketoximes. Let us compare all the three stereo descriptors One is the cis-trans descriptor, another one is a SynAnti, the last one is EZ. So how do these three assignments compare? Let us start from the cis-trans. The cis-trans can be assigned to both sp3 hybridized carbons and sp2 hybridized carbon. So we already saw the sp2 hybridized carbon. If it is a cyclic system, then we say it is a sp3 hybridized carbon. There also we can assign cis-trans isomers. Basically, if you take a cyclohexane, we will be studying about in the conformational isomerism more about what is cis-trans isomerism. So I am not discussing that elaborately here. So we will study about 1 to 1,3 arrangements, whether they are cis or trans, in the later part. In the case of SynAntinoisomers, this generally occurs in the sp3 hybridized carbon atom. The only exception is the oximes. So except oximes, all the SynAntinoisomers are assigned to sp3 hybridized carbon atoms only. And in the case of EZ nomenclature, this occurs only in the case of sp2 hybridized carbon atoms, or the alkenes double bond only we can assign EZ nomenclature. So as we mentioned, the cis-trans is basically applicable to double bond if it is the sp2 hybridized carbon, or the cyclic system is basically if it is a sp3 hybridized carbon. And the SynAnti we can assign to both open chain and the cyclic systems, whereas the EZ is for the double bond. So the double bond can be in the open chain or it can also be in the cyclic systems. So this is how EZ nomenclature can be assigned. And in the case of cis-trans isomers, the same groups or the same moiety is present on adjacent carbons, that is the sp2 hybridized carbon atom, that is across the double bond, or on different moiety, that is what we have seen in the zigzag arrangement. It can be on the neighboring carbons, or it may also be in the faraway carbons in the case of sp3. So cis-trans can be assigned to these two type of arrangements. In the case of SynAnti, basically we can assign to either adjacent carbons or faraway carbons. But in the case of EZs, this is basically the same group or the adjacent group present only on the adjacent carbons. That is across the double bond only we can assign EZ nomenclature. And both the cis-trans and the SynAnti is basically a relative stereochemistry, whereas EZ nomenclature is generally an absolute stereochemistry. We can assign them. That means when we say this is a relative stereochemistry, we have to actually arbitrarily assign whether the groups are on the same side or on the opposite side. There is nothing called absolute arrangement. These are basically relative terms, because if both the groups are on the same side or on the opposite side, so this is arbitrarily assigned. The same way SynAnti is also assigned arbitrarily, but in the case of EZ nomenclature, we generally follow the CIP rule, that is a Kahn-Ingold per log rule. So this is a more accurate one, or an absolute assignment of stereochemistry. And in the case of cyclic systems, basically the ring flip does not change the cis-trans isomers. So the cis isomers, even after ring flip, remains as a cis isomer. Trans isomer also remains the same. So ring flip does not change the relative arrangements of the groups. In the case of SynAnti, basically this can also be used to describe the nature of transformations in the case of additions and eliminations. Basically we have syn addition and trans additions, or the anti-additions. We also have syn elimination or anti-elimination. So these are a couple of terms which we will be studying in this particular and the couple of other sessions also. So the SynAnti can also be used to mention how the reaction actually proceeds, whether it is a cis addition or the syn addition. Say for example, you take a hydrogenation, a metal catalyzed hydrogenation generally goes via syn addition, and the bromination reaction sometimes, most of the times, happens via the anti addition. So these are some of the standard ways by which we depict the stereochemical outcome of a particular transformation. With that, we conclude this session on geometric isomerism. Thank you. In summary, let us recap what we have studied so far. We studied about what are geometric isomers and geometric isomerism, how to name the geometric isomers using either cis-trans nomenclature or EZ nomenclature or SynAnti nomenclature, and how the relationship exists. Basically, the cis-trans isomers can be given to adjacent carbon atoms or faraway carbon atoms, and whether it involves sp2 hybridized carbon or sp3 hybridized carbon. And we also studied about the comparison between all the three types. So with this, we conclude the session on geometric isomerism. Thank you.